Hi, my name is Seth Adams, and this is my video for Physics 2211, Lab Number 1. So the contents of this video is going to be the introduction. That's what you're listening to now. I'm going to go over the physics principles of this experiment, the experiment itself, the computational model to go with it, analysis of all the parts before this, and some questions to finish. So what was the purpose of this lab? The purpose of this lab was to explore motion under a constant velocity. Doing that, we utilized the Tracker app for video analysis of our data. We developed a computational model in GlowScript based on Newton's laws, which the two we focused on were the first and second, but mainly the second for this experiment. Examine the two methods of studying constant velocity. So here are graphs from the experiment. This top one with the red line, this is our data from the Tracker app. And we have one little point up here in the corner that, it is an experiment, so there's going to be human error, and that's where this point came from. But other than that, it looks pretty similar to our GlowScript code, which is the computational model directly up under it. When we put them together and compare them, we can see that they are not the same. The principles we learned in today's experiment were Newton's first and second law, constant velocity, and iterative prediction. Doing this, we use the velocity update formula, which states V of F, which is velocity final, plus V of I, velocity initial, plus F of net over M times delta T. In this lab, we're assuming that there are no outside forces like friction working on the rolling object. Because of this, the golf ball roll at a constant velocity from start to end. And, this is in a perfect world where friction doesn't exist, where it does when we run this experiment in real life. So right here is the video we put on Tracker. Here we have our Tracker model where we're running the golf ball through it along this x-axis from 0 to 1 meters. All right, and moving on from that, we have our computational model code. We did this in GlowScript, and these are screenshots of what we did. The ball position vector we have set at 0, 0, 0, which is the origin. And the ball velocity vector we have set at negative 0.00428. Our number is negative because we are rolling the ball the opposite direction of what everybody else has done so far. So that throws our numbers off a little bit. Here is our program running. As you can see, the ball is rolling to the left, and it matches our graph where the graph is going down and to the right. In this experiment, I mentioned it earlier, but there are plenty of sources of possible error. Some of these things are friction. When friction is present, which it is in our Tracker experiment, it will slow down the golf ball and it will not remain at a constant velocity because of the friction. Another problem that could arise is mouse accuracy when we were clicking the center of the ball's mass of Tracker, which that's just a human error thing, like my fourth point here. And the video angle, because of the angle of the video not being perfectly square, that could also have thrown off our data a touch. A few of the questions here, what if we were to flip axes and x became negative? If our axes were flipped, our graph, which was going this direction, would switch to this. All other forces have been removed from our consideration. The only forces left to be considered are the force of the golf ball rolling on the table and gravity. Some similarities and differences between the data and the model that we noticed. Both have the same starting velocity, and both experiments move in the same direction on the coordinate plane. Compared to our model, though, our tracker data shows that the ball began to slow down as time progressed. This was caused by the friction of the experiment